introduction. Okay. All right. So we're gonna do basically our start for differential equations today, right? So we're gonna do both 1.1 and 1.2 together. It just makes sense to do both at the same time. Um, and then we'll. It's a lot of just definitions, right? That's the focus of 1.1 and 1.2. And so let me write out the title. So 1.1 and essentially 1.2. It's our introduction to differential equations. Now, by the way, if you do have questions, you can always type your questions on the chat, or you can unmute your mic and then sort of ask it on video as well. Um, so you can do either one if you have any questions. I do expect you to answer back. So if I ask certain things, then you can sort of type the answer on the chat as well, or just say them as well by unmuting your mic. Um, but those, so make sure you do that when you have questions, though. Okay. All right. So let's talk about differential equations. So what exactly is differential equations? The easiest way to define what a differential equation is, it's an equation, obviously, that has derivatives on them. And so it's an equation involving derivatives of your functions. Okay. And that's what differential equations are, right? So differential equations diff eq for short, right? And so that way we don't have to keep writing differential equations all the way through. But the formal definition on it is basically an equation involving the derivatives or partial derivatives of a function. So any equation involving the derivatives of a function. So for example, dy dx, right, is equal to 3x plus y. Right? So that is a differential equation, right? So it's an equation that has a derivative on it. Now, by the way, the derivative does not have to be the first derivative. It could be any order derivative. So you could have something like this. So that is also a differential equation. Okay. In this one, though, it involves a second order derivative. Now, partial derivatives, again, I know most of you, or I think most of you, have never taken multivariable functions before. So this might not be something you're used to, but this sort of just means it's your regular derivative, but now it's a multivariable function. So it looks something like this. So these are partial derivative symbols, okay? And basically having those means you have a partial differential equation. Okay. Now, over here, okay, since the derivatives involves a single variable functions, these are called ordinary differential equations. Okay. So since they involve single variable derivatives, or single variable functions, I should say, then they are ordinary differential equations. So this one right here is called a partial differential equation. Now, as far as what our class is concerned, we're only gonna deal with this one. Okay. Now, for short, by the way, we call this ODE. Right. So ordinary differential equations. Okay. Questions? Okay. All right. Just more definitions here. So going back to the ordinary differential equations, since this one only has the first derivative, this is called a first order differential equation. Like it only has the first derivative on it. This one, since it contains the second derivative, this is called a second order derivative. All right, so for our first few examples, okay. All right, so I want you to find the order of each ODE. So for each ordinary differential equation, find me the order, right? So, so number one, okay, 3x plus 2 dy dx is equal to sine x. Okay. Number three, number two, sorry. Okay. Um, an x double prime minus a 6x prime. Okay. Minus a 16x is equal to 0. Okay. And number three, okay, a y superimpose or superscript 4 in parentheses to the 3 halves power. Okay. Minus 2y double prime is equal to cosine x. Okay. So now, whenever I give you an example, I usually pause the recording, right? So this is for people that are going to watch this later. So I'll pause it, okay? But then essentially, I'm basically giving you time to actually work the examples out, okay? So for this one, just find me the order for each one. So again, it should be pretty quick. This is not a difficult sort of example. So what's the order of example number one? First. Okay. How about number two? Second, right? And how about number three? It's a fourth, right? That's what this means, right? So this is a fourth derivative. This is the symbol we use if it's higher than a third derivative, because anything higher than three, those prime notation becomes confusing. It's a lot harder to count. And so we use this notation for derivatives. So this is the fourth derivative. So this is a fourth order differential equation. Okay. Any questions on it? Okay. All right, now the next definition. Okay. So for this one, suppose y is our function, right? So suppose y is a function of x, right? So y is our function, okay? So then a differential equation is said to be linear okay, if the unknown function which in this case is y, and its derivatives okay, appear as linear functions. I should say linear expressions. And so remember, linear expressions can only be multiplied by a constant, right? That's it. So your focus is whatever your unknown variable is, and you want to make sure, and its derivatives, that each one of those have a linear expression associated with it. And so, for example, here, so for the first one is linear because the only y is this one, dy dx, and it's simply multiplied by a constant, which in this case happens to be 2. So same goes with this one, right? So this one, x, is your function. So x is unknown function. So each one of its derivatives and the x itself is only multiplied by the constant or a constant variable. So in this case, then x is also linear, right? So this one right here is a linear differential equation. This is not linear because of the 3 halves power. So a y to the fourth has an exponent other than 1, then that means that is not linear. Okay. Questions? So on the next example, okay, the next examples, I don't think I can fit it here. Maybe I could. Okay. So in this one, all I want to know is it linear or not linear? And so tell me each one of these equations are linear equations or linear differential equations or non-linear differential equations. Okay, so number 4. Okay. So the first one, so y double prime minus 3y prime plus a y squared equals 0. Number 5, okay. The third derivative plus a y times y prime, okay, is equal to x squared. Number 6, a y double prime plus a 3y prime minus an x squared y is equal to 0. So again, I'm going to pause the recording as you sort of determine if each one is linear or nonlinear. All right, so again, these are not sort of law examples, right? I'm basically not asking you to solve anything else. Just tell me if it's linear or not linear. First one, linear or not linear? Linear. Anyone else? So it's actually not linear. Can you tell me why it's not linear? The y squared, right? Remember, y is your function, so y is what you're interested in. So the y has a square in it. So the fact that it has a square, it's quadratic, right? That's what makes it quadratic. But it's obviously not linear anymore. So hence the equation is not a linear differential equation. How about number 5? Linear or non-linear? Non-linear, right? So why is it not linear? Okay, so it's not this one. Okay, it's not because of this one. This means the third derivative. So this is not y to the third. This is the third derivative of y. So this is not why this is not linear. This is why this is not linear. It's kind of like having a y times y, which is a y squared, but you just obviously it's not y squared because one of them is the first derivative, but you are multiplying two y's. So multiplying two y's, essentially the degree is 2. So this is not linear. This one is though, right? So this expression is linear because that's just